Hello. We are going to talk about another viewpoint of scalar diffraction theory, and that is the angular spectrum method. And we are going to have a different viewpoint, which is quite distinctive from the former description based on Kirchhoff and the Rayleigh-Sommerfeld theory. So let us try to think about some this schematics. Let's say in previous case, we have a certain plane, and then we have an aperture, and of course it is all black. And then what we have assumed is that we have some kind of a point-like source, and then each point-like source emits a spherical wave. And that is the basis for the Rayleigh-Sommerfeld or Kirchhoff. But in the case of an angular spectrum method, we have a different viewpoint. So we have a certain aperture here, and then as we have seen here, if the complex field distribution over monochromatic disturbance is Fourier analyzed across any plane, the various spatial Fourier components can be identified as the plane waves traveling in different directions away from that plane, so that we have another plane here. Let's say z equal to 0, and from here to here is z. Let's assume that is the parallel plane. And then what we are going to see is that there would be some kind of Fourier component here. Let's say in the kx, ky. And then, of course, there is something, it is propagated in this direction. So what is going to assume here is that in each direction, we have assumed a plane wave, okay, like this, so that various spatial Fourier components can be identified as plane waves. Okay, that is the big difference. Here is the spherical wave, and there's a plane wave. And that's the big difference between those two attitudes. So today you are going to talk about this part, which is the angular spectrum method. Okay, so that's the key point we are going to pursue. So in this case, let the complex field across the z equal to 0 plane be represented by the uxy0 here. So z equal to 0, and then the field component or scalar field is given at that plane. Okay, our objective is to calculate the resulting field uxyz away from but the parallel plane distance z. So let's see what we have learned here. This is the case. So across the z equal to 0 plane, the function u has a 2D Fourier transform given by. So at the z equal to plane, we have this uxy0, and then it can be Fourier transformed in two-dimensional space, fx and fy, and then this will give you fx, fy at z equal to 0 here. And then what we are going to talk about later on is that we are going to have this Fourier transformation, and then we are going to have an inverse transformation. So the A is given in terms of a Fourier transformation, then U is given by inverse transformation of this A. Okay, and then what we are going to do furthermore is that we are going to identify the wave vector k. So when we say the plane wave, that means there should be some kind of a wave vector k that will define the direction of a plane wave propagation. And then here we are going to define alpha, beta, gamma as, in this case, if there is a k vector, wave vector, and then we have an angle with the axis alpha, the angle between the k and the y-axis is beta, and the angle between the k and z is gamma. And then alpha, beta, gamma will give you the k directions. So so it's a simple plane wave. Plane wave is a unit amplitude. Assume that this is the unit amplitude, and then this is the direction of a propagation, and then this is the monochromatic frequency. Okay, so this is the plane wave. That's all we know. Okay, and then here is the position vector, which is given by this vector form. And then in this case, k is given by 2 pi over lambda alpha x beta y gamma z. Okay, so in other words, alpha, beta, gamma will give you the directional cosine. And then assuming we have a monochromatic wave, so monochromatic, that means we already know how it's going to change. Is going to change like as it here, e to the minus 2 pi ut I. Okay. So we don't have to worry about those time dependence, and so we can just drop. And then we come up with a spatial component, which is given by this one. And then because of the directional cosine, and that this is the unit vector given by this magnitude, and then we should satisfy this UDT. Gamma should be square root over 1 minus alpha square minus beta square, or you can say that simply alpha square plus beta square plus gamma square should be 1, because this is the magnitude and this should be unit vector. And its magnitude, this is the magnitude, should be 1. Okay. Across the plane z equal to 0, this component may be regarded as representing a plane wave propagating with the direction cosine. Alpha is lambda fx, beta is lambda fy, gamma is this function. Okay. So let's go back what we have already known here. Okay, so we have this Fourier component, uxy0 is given, and then we have this Fourier component. Okay, and then we have uxy0 is given in terms of a Fourier component times this exponential term. And then what we can say is that this field component at the z equal to 0 it just looks like a kind of a plane wave, right? Plane wave with this amplitude, and its amplitude its direction cosine is given by fx and fy, which corresponds to cosine the angle alpha and beta. Okay, that's the starting point. So across the plane z equal to 0, exponential I 2 pi fxx plus fy may be regarded as representing a plane wave propagating with the directional cosine, this one and this one. Okay, here gamma should be this one. In the Fourier decomposition of U, the complex amplitude of the plane wave component with the spatial frequency is this one, okay? Evaluated at this one. For this reason, the function here is represented in this integral form is called angular spectrum of disturbance uxy0. So it's the same name, but in some cases we are using the Fourier component. So let's say the fx fy, and then we call it Fourier transformation of uxy0. But at the same time, we call it the angular spectrum of the disturbance uxy0 in terms of plane wave. Plane wave, this alpha and beta, gamma. Okay, that is the starting point. And then consider angular spectrum of u across a plane parallel to the xy plane, but at a distance z from it. Okay, so that what we are going to do is that we are going to look at this component. Okay, and then this is nothing but we are going to do the Fourier transformation. And then remember that here x, y, z, z, same component. Okay, so remember that this is not the k or the fz. Okay, so note that you can be written as uxyz is given by this one. Okay, and then what we now know is that once we know this, and it's the summation of plane waves at each angle, and then we summed of the angle. Okay. And then we can further simplify this integral equation, recalling that Helmholtz equation. Okay, so k is the wave vector. Then A must satisfy the differential equation. This. Okay. So remember that this is the z component and the z. Okay. So if you do the Fourier transform, this Helmholtz equation, the Laplacian is nothing but okay. So we have the uxyz has this dependence, so that when you take the double partial integral, then this part comes out, and then if you take the double integral for y, this vector comes out. Okay, and then you have a normalization condition such that we get the 1 minus alpha square minus beta square like this, and then we get these differential equations. So this is the important. We have this how the A will change with the Z, and this will give you the clue how the A will change with the Z for given alpha beta. Okay, and then we have this is the well-known ordinary second order equations. So this is nothing but remember that something plus something A equal to 0. So that depending upon the sign of this constant, we can have a two condition. One is the exponential I or exponential plus minus. Okay. So an elementary solution would be this if this is the positive number. So as long as alpha square plus beta square is less than 1, then this will be our solution. Remember that we know what it is. We know what it is because this is given. Then when you do the Fourier transformation, we have this one. And then of course, we can change the variable like this. And then we get the angular spectrum at z equal to 0. Okay, so this is the very important viewpoint. If you look at it, this is the alpha over lambda, beta over lambda. In other words, this is the Fourier component, fx and fy, but this is the spatial coordinate, z. Okay, so what we want to know is that once we know the z for arbitrary z, and then we can find out uxyz. Okay, for once we know this, we do the angle integral for this term, and then we get this one. And in order to find this, we know that A will satisfy the Helmholtz equations, and then as a result of it, we get this very simple second order differential equations. And the solution would be if alpha square beta square is less than 1, we get this exponential I term. And then if alpha square plus beta square is larger than 1, then we have this exponential term. Okay. So we have two solutions, and then we call this is the evanescent wave because it will die away as z is increasing. As z increases, and this term will die away, and then it does not contribute too much in the far field. And if this is the case, then we have an oscillating term, and then this will contribute to our calculations. And then let's try to think about some more detail. So define an amplitude transmittance function. We are going to use this term on and on in the latter section of this course. And the amplitude transmittance function is defined as a transmitted a scalar field over incident scalar field. Okay, so that this will define the transmittance. And then use the convolution theorem to relate the angular spectrum AI of the incident field and the angular spectrum AT of the transmittance. Okay, so if you look at it, UT is simply multiplication. And remember that here, UT, TA multiplied by UI, X, Y, 0. Okay. Okay. And remember that in the convolution theorem, we have learned that convolution, let's say f g in real space, if you do the Fourier transformation, then it is simply multiplication of this one. So here the Fourier transform of small f is capital F, a Fourier transform of the small g is capital G. And the same manner, if we have in real space, when you do the Fourier transformation, and we get G, okay? So here is the case. In real space, we have a multiplication. And then when you do the Fourier transformation, and then we get this one, okay? So it is nothing new. You have already known about this, but this is very important. What we are going to talk about here is that the transmittance angular spectrum is convolution of incident angular spectrum and the transmittance. And here, transmittance, the capital T is not identical to the small capital A, TA, and then it is given by this function, okay? And it's nothing but the Fourier transformation, right? Fourier transformation, okay? So what we are trying to do now is that for the case of a unit amplitude plane wave illuminating the diffracting structure normally, in that case is we have a AI is the delta function, okay? And then AT is given by this one is this one, okay? The transmitted angular spectrum is found directly by Fourier transforming the amplitude transmittance function of the aperture. Okay, this is the direct relationship for the case of a unit amplitude plane wave. Okay, and then what we are trying to do next is that based upon this one. So we go back to original equations. Once we know this angular spectrum, of course this can be written in terms of alpha, beta, d alpha, d beta. But for the time being, let's assume that it is written in terms of a Fourier transformation. And then what we are trying to say is that we know that AFX and FYFZ is in fact like this, okay? So at z equal to 0, we should think about incident field and the transmitted field. Incident field and the transmitted field. And then this will be the phase factor that will add it on for arbitrary z. So we are going to talk about transfer function, but for the time being, let's assume that this is a kind of a function, we call it transfer function. This is just the name, but we will see later on. So in the case of a free-space wave propagation, we have this transfer function, capital H, okay? And then the propagation phenomenon may be regarded as a linear dispersive spatial filter with a finite bandwidth. The transmittance of the filter is 0 outside the circular region, radius of lambda inverse in the frequency plane. And within the circular bandwidth, the modulus of transfer function is unity, but the frequency-dependent phase shifts are introduced. Okay, so the angular spectrum approach and the first Rayleigh-Sommerfeld solution yield identical prediction of the diffracted field. So basically, the angular spectrum and the Rayleigh-Sommerfeld solution is in fact mathematically identical, but we have a different viewpoint. Okay, so what I like to say is that the importance of two outcomes. One is we start with this very simple Fourier transformation. But if you look at it, it's not that trivial. If you look at it, it's the Fourier transformation on fx and fy. But the z dependence is something else. Z dependence is something else. And Z dependence is actually either this one or that one. Okay. And obviously the surviving term would be this one. Okay. Because this one will die out with this evanescent wave nature. So what we know is that once we know the angular spectrum at z equal to 0, angular spectrum at z equal to 0 plane, and with this propagation factor, and which we call it transfer function. So at z equal to 0 here, and then as wave propagates, we have to add this transfer function to get arbitrary field at the z equal to 0. Okay, so note that angular spectrum at the z equal to 0 plane here is directly related with the scalar field at the z equal to 0 plane, which is nothing but the Fourier transformation, two-dimensional transformation with the change of a variable. But remember that alpha and beta corresponds to this angle. Alpha and beta is this angle. And then we know that this will give you the directional cosine. And then we can we can imagine that this alpha, beta, and gamma will determine the direction of a wave vector or plane waves. Okay, so that we have various plane waves for different alpha and beta. Okay, depending on the initial scalar field at the z equal to 0, and then we can find out this one. Okay, or by noting that the z dependence is given by this one, we have this factor. Okay, this is our solutions. So once we know angular spectrum at z equal to 0, then everything is solved with this transfer function and routine two-dimensional Fourier transformation. Okay, and this is, in fact, if you look back, it is very identical to the Rayleigh-Sommerfeld, the first law. So we are going to use both angular spectrum or Rayleigh-Sommerfeld in the following sections. So we'll be seeing, I'll be seeing you in the classroom. Bye now.